Hello.
Hola, ¿qué
Hello.
tal?
Hi.
Good morning. Today we are going to dive a little deeper into how graphs of functions work. So we see graphs of functions all the time, and we're pretty familiar with what makes each one distinct. But how do we know what a function is going to look like? Why is a quadratic function shaped like a U? Why does a cubic function look like whatever this is? I'll give you a hint. It has something to do with the equation of each function. See how this sounds to you. Graphs of functions are a visual representation of what happens when you solve for y. Here's an example. Let's say we want to graph a quadratic function like just x squared. So we make a little table, we have a graph. So in order to do this, let's pick some random x values that we'll plug in. I'll fill out the column on the left, and we're just going to go through one by one and see what happens when we plug in each x value to the equation and solve for y. So we'll start with -2. If I plug that into x squared, that means it's going to be -2 squared, which we know ends up being 4. So that means that the point -2, 4 is going to be on the graph of the equation y equals x squared. And that's how all of these points are going to work. So we have -1, that means we're plugging -1 into our equation. -1 squared is 1, so the point -1, 1 is going to end up on our graph. Next two points are the same, 0, 0, 1, 1, and finally 2 squared is 4, so that means that the point 2, 4 is going to be on our graph. If we connect the dots, you'll see that the familiar U shape starts to emerge, and that's where that shape comes from. It's just the result of plugging in all those x values to a quadratic function. So this can be really helpful because this is how the graph of every function ever works. Sometimes we have little tricks and shortcuts that we use to make graphing faster, like with slope-intercept form, starting with the y-intercept using the slope, but you can always just plug a few x values in, solve for y, and verify your graph that way too. Let's say we're trying to graph the quadratic equation x squared minus 3. So without even knowing what the characteristics of quadratic graphs are or what a parabola is, I can tell you a point that I can guarantee is going to be on that graph. Let's try plugging a 2 in. So if I'm plugging a 2 in, that means x is going to be 2, and so I'll substitute that in there and just go 2 squared is 4, 4 minus 3 is 1. That means that the point 2, 1 is guaranteed to be on the graph of that quadratic. Because if I plug in the x value of 2, I get the result of 1. That means 2, 1 is on the graph. So if a point is going to be on the graph of an equation, that means that you should be able to plug in the x value and get the y value as a result. So back to this example we have. If I graph it, here it is, you'll see right there, there's the point 2, 1. It has to be on there because that's how that entire curve was created in the first place. Every single one of those points comes from plugging in an x value and getting that specific y value as a result. So this idea can be really helpful, and especially in maybe like multiple choice problems, which are pretty common in math. Let's say you're being asked to identify the graph of the equation y equals x squared plus 4x minus 5, and they give you these 4 graphs here. Maybe you think, I know a trick. See that -5 at the end? That means that the y-intercept of the graph is going to be -5. And you look and you say, well, there's an intercept of -5, there's an intercept of -5. That's not going to work. What else can we do? Well, why don't we just plug something easy in? Like 1. All right. 1 squared plus 4 times 1 minus 5. 1 squared is 1. 4 times 1 is 4. 1 plus 4 minus 5 is 0. What that means is that the graph of that equation right there is going to have the point 1, 0 on it. It has to. And if we look one by one, this one's not going to work. It's pretty close, but I don't see the point 1, 0. This one, not even close. This one looks like it's got it. Let me make sure that the last one doesn't. Nope, no way. And there we go. That has to be the graph of the equation that we were given. None of those other graphs are even possible because they represent combinations of x and y that don't come from that equation. I need to be able to plug in every single x value I see and get the y value that I see as a result. And if that's not true, then that graph is not correct. So as you continue to work with different functions and different equations, keep that in mind. Hopefully this video helped you see why the graphs of different functions look the way they do, since every graph just represents what happens when you plug in x values and solve, and also how you can quickly identify whether a graph matches an equation or not just by picking an x value to plug in and finding the graph that represents the correct y value as a result.